Welcome to the deep dive. You know, whenever you take a picture with your phone, you probably feel like you're capturing reality.
Oh, for sure.
Right, like you point the lens, you tap the screen, and boom, there it is, a frozen moment in time.
Yeah, and it definitely feels, comprehensive to the human brain. We are very conditioned to just accept that flat image as the absolute truth of the moment.
We really are.
Yeah.
But then you stop and think about it, and you realize you haven't actually captured the reality of that moment at all.
Not even close.
No. You've taken this complex, living, three-dimensional world and just, like, smashed it flat onto a two-dimensional grid of pixels. It is essentially a compression of truth.
That's a good way to put it.
And we just accept it because it's convenient. Which brings us to the core mission of our deep dive today.
Yeah.
Because for anyone listening who loves technology, you hear this specific word thrown around constantly.
I know exactly where you're going with this.
Right. In sci-fi movies, in tech marketing, even just walking past displays in shopping malls. Yeah. The hologram.
The magical hologram.
It promises to break that two-dimensional flatness. But if you stop and ask someone, physically speaking, what actually is a hologram, the answers you get are, well, incredibly murky.
Murky is probably an understatement. I mean, the vast majority of what you see out in the commercial world being labeled as a hologram simply isn't one.
Really?
Yeah. The term has been completely hijacked to describe almost any optical illusion that looks slightly three-dimensional.
So we're going to fix that today. We're going to completely strip away the marketing hype and the parlor tricks. We are utilizing a comprehensive expert analysis document that breaks down the actual fundamental physics of holography.
And it is fascinating physics.
It really is. We'll track how it moved from, old school laser laboratories into the modern digital age.
Yeah.
And we're going to explore the surprising ways it's quietly revolutionizing high-stakes industries right now. Okay, let's unpack this. We need to start with the baseline definition.
Let's do it.
What makes a true hologram physically different from that flat photo on your smartphone?
Well, to get to the bottom of that, we should probably look at the Greek roots of the word itself.
Okay, Greek roots.
Yeah, so holos translates to whole, and graphene means to write.
Whole writing.
Exactly. Holography is the science of writing the whole picture. See, when your phone camera takes a picture, its internal sensor is only recording a single property of the light bouncing off a subject.
Just one.
Just one. It records the intensity, which we perceive as amplitude or, brightness. It completely discards the physical distance that light traveled to reach the lens.
So the depth data is just thrown out.
Completely lost.
Let me try an analogy here to see if I'm grasping this. If we compare photography to recording an orchestra.
Okay, I like orchestras.
Normal photography is like an audio recording that only captures the volume of the symphony. Like when the music is loud, when it's quiet, but you get absolutely no other information.
Yes. Let's take that analogy a step further, actually. If the volume is the light's intensity, then the pitch of the instruments would be the light's wavelength or color.
Okay, so camera captures volume and pitch.
Right. But true holography captures the volume, the pitch, and something called the optical phase.
Optical phase.
Yeah. Imagine sitting blindfolded in that symphony hall. Phase is the precise microsecond timing of the sound waves hitting your ears from different directions.
Yeah, oh, wow.
Yeah. That minuscule difference in timing is what lets your brain know the violins are sitting 20 feet to your left and the cellos are 10 feet to your right.
So by recording that optical phase, a hologram captures the exact spatial location of where the light originated.
It records the exact timing and structure of the light wave itself. And, recording that phase is the fundamental key. It's what allows the reconstruction of a three-dimensional image with genuine relief and parallax.
And parallax is that effect where if you move your head left or right while looking at a physical object, you can see around the sides of it. A true hologram does that.
It does. Absolutely.
That's wild.
Because the reconstructed light hitting your eye is behaving in the exact same physical manner as it would if it were still bouncing off the original physical object.
I am stuck on the mechanics of this, though. You can't just snap a normal shutter and capture phase. Like, how do you actually record the timing of a light wave?
You have to create what physicists call an interference pattern.
An interference pattern.
Right. You need two separate sources of light. First, you have an object wave, which is the light bouncing off the physical item you want to record.
Okay.
Second, you introduce a reference wave, which is a pure, coherent laser beam. You aim both of these waves so they overlap.
They literally crash into each other.
They do. Where they meet, they physically interfere with each other, creating a microscopic terrain of light and dark ripples. You record that raw ripple pattern on a highly sensitive surface.
So it's not recording an image of an apple. It's recording the crash of two light waves hitting each other after one of them bounced off an apple.
That is a very accurate way to visualize it, and the crucial step happens later.
When you look at it.
Exactly. When you illuminate that recorded pattern of ripples with the exact same reference laser, the pattern physically bends the light. It diffracts it.
Diffracts it.
Yes, that diffraction perfectly recreates the original object wave traveling through space.
Okay, so the sources mentioned this underlying physics was discovered a really long time ago, like back in 1947 by a physicist named Dennis Gabor.
Yes, Gabor.
But he wasn't even trying to invent 3D photography, was he? He was working on electron microscopes.
What's fascinating here is how often monumental discoveries are born out of sheer frustration with an unrelated problem.
Right.
Gabor was trying to improve the resolution of electron microscopes, and in the process, he figured out the mathematical foundations of this whole writing. His math was so groundbreaking, it eventually won him the Nobel Prize in Physics in 1971.
Wow.
But in 1947, he hit a massive technological wall.
Because lasers didn't exist yet.
They did not. And you absolutely need pure, highly coherent light for those interference ripples to be sharp enough to record. So holography essentially sat dormant in academic papers as a mathematical curiosity until the 1960s.
When the laser was finally invented.
Exactly. Once researchers like Emmett Luth and Juris Upatniks got their hands on lasers, they were able to produce the first tangible, physical 3D holographic images.
In reading through the history, there were two main methods back then. Transmission holograms, which required you to shine a laser completely through the film to see the image.
Very complex setups.
Yeah, and reflection holograms, where the light bounced off the surface. The reflection ones were a big deal because you could view them with just a regular white light bulb, without needing a laser lab.
True, but even with reflection holograms, the creation process was incredibly tedious. I mean, for decades, the field relied on heavy, vibration-free tables floating on compressed air just to prevent microscopic movements from blurring the ripples.
Loading tables.
Yeah, and you had to use chemical photographic plates and develop them in a darkroom. It was an analog, painstaking endeavor.
Which logically leads to the digital leap. I mean, we don't use chemical plates for normal photography anymore, so obviously holography had to go digital as well.
Naturally.
The document outlines a field called digital holography, or DH. And I really want to understand how this transition happened because it feels like there is a missing link here.
Okay, missing link.
Yeah, like if we can put a 4K digital camera inside a smartphone today, why do we not have smartphones projecting room-sized holographic scenes onto our living room floors?
Well, the transition to digital holography was conceptually brilliant. The idea was to replace those chemical plates with digital camera sensors.
Right, like the ones on our phones.
Specifically CCD or CMOS chips, yeah, to record the microscopic interference pattern. Then, instead of shining a physical laser to reconstruct the image, scientists realized they could use computational power.
Oh, interesting.
They wrote algorithms to simulate the physics of the light diffraction, calculating the 3D field entirely mathematically.
That eliminates the darkroom and the physical lasers for viewing. You just record the data and let a computer crunch the numbers.
Exactly.
But the expert analysis points out a massive bottleneck holding this back. It cites the Nyquist sampling theorem. Now, I've heard that term in audio engineering, but I don't quite grasp how it physically limits a visual hologram.
Let's break it down. Think of trying to draw a highly detailed checkerboard on a piece of paper, but the only tool you have is a thick, fat, permanent marker.
Okay, fat marker, tiny checkerboard.
Right. If the squares on the board you're trying to draw are physically smaller than the tip of your marker, you cannot draw them.
No, the ink just bleeds together and you get a blurry gray smudge.
Precisely. The tool is too blunt for the detail.
I see.
In digital holography, our digital camera sensors are the fat marker, the pixels on those sensors are the tip of the pen, and those interference ripples we talked about, the collision of the light waves, are the tiny checkerboard squares. The Nyquist theorem essentially states that to capture a wave accurately without turning it into a distorted smudge, your digital pixels must be at least twice as small as the wave detail you were trying to record.
Okay, I'm following that. But the document mentions this distortion is called aliasing, and it's heavily dependent on the angle of the lasers. How does the angle change the size of the ripples?
Well, when the object wave and the reference wave meet, the wider the angle between them, The tighter and smaller the resulting interference ripples become.
Oh, so wider angle means smaller ripples.
Exactly. To keep those ripples large enough for our current digital pixels to actually see them without aliasing, the angle between the lasers has to be incredibly narrow. We're talking about just a few degrees.
Wait, so are you saying we are literally just waiting on the digital camera industry to invent microscopic pixels before we can get massive room-sized holograms?
That is the harsh reality of the physics. We are physically constrained by the manufacturing limits of silicon. And it's not just the recording sensors either.
It's not.
No, it also limits the hardware that would project these images, which are called spatial light modulators, or SLMs.
SLMs. The document specifically mentions LCOS devices in relation to this. What role do they play?
LCOS stands for liquid crystal on silicon. They're a type of spatial light modulator used to alter the phase of light on demand.
Okay.
In digital holography, LCOS devices are incredible for dynamically correcting optical aberrations. If a holographic projection gets distorted by an imperfect lens, an LCOS device can actively reshape the light wavefront to cancel out the distortion.
That's super useful.
It is. But just like camera sensors, these SLM are still bound by pixel density. Because we can't make the pixels small enough yet, true digital holograms can only be recorded and projected if the object is very small or placed very far away.
Which severely chokes the field of view.
It absolutely chokes it.
That feels incredibly limiting for consumer tech. Like, we have the underlying math, but our silicon hardware just cannot handle the density required for a wide field of view.
That's the current bottleneck, yes.
But if we can't project giant dynamic scenes for entertainment, how is this a multi-billion-dollar industry? Because the source material spends a massive portion of its page count discussing industrial applications.
If we connect this to the bigger picture and look past the desire for entertainment, holography is an absolute industrial workhorse.
Really?
Oh yeah, and it relies heavily on a technique called holographic interferometry.
Okay, I am going to need you to walk me through how that works in practice because the terminology sounds pretty dense.
Fair enough. Let's consider a practical scenario. Imagine you have a physical object, say a freshly manufactured metal component for an aircraft.
An airplane wing part.
Sure. You use lasers to record a precise digital hologram of that metal piece in its resting state. We'll call that state time 1.
Okay, so I have a perfect phase-exact digital record of the metal.
Now, at time 2, you take that real physical piece of metal and you put it under a tiny amount of stress. You might apply a slight temperature change or just a bit of physical pressure.
Just a little nudge.
Right. Then, you overlap the live light coming off the stressed physical metal with the original holographic recording from time 1.
Oh, wow.
Because the real metal has deformed microscopically, the light waves no longer match perfectly. They interfere with each other, creating visible bands of light and dark across the surface of the object.
The document calls those bands interference fringes. But I'm having trouble visualizing the scale here. If a thick piece of aerospace metal is just under a slight temperature change, how much is it actually bending? And how do light fringes measure that?
The scale is what makes this so revolutionary. These fringes act like a topographical map of microscopic stress. We're talking about detecting structural shifts down to a fraction of a micrometer.
A fraction of a micrometer?
Yes.
To put that in perspective for you listening, a standard human hair is roughly 100 micrometers thick. So this technique is mapping out structural warping that is less than 1/100th the thickness of a hair.
Exactly. And if we connect this to the bigger picture, think about what happens when you board a commercial flight.
Right.
You're trusting a massive structure made of complex composite materials that endure immense dynamic stress. How do engineers guarantee a newly manufactured composite wing doesn't have a microscopic pocket of air hidden deep between its layers?
You can't just crack the wing open to check.
No, you destroy the wing just trying to test it.
Exactly.
This is where holographic non-destructive testing becomes vital. They can map static deformations by looking at how those interference fringes warp around hidden defects.
That is so smart.
And they go much further than static tests. Engineers use a technique called holographic vibrometry. This allows them to perform modal analysis on vibrating structures in real time.
Wait, real time?
Yes. They can literally watch the microscopic resonant waves rippling across a jet engine casing while it's under dynamic active vibration, ensuring there are no hidden fractures waiting to fail.
That is wild. But going back to the hardware problem, if standard digital camera pixels aren't dense enough for large-scale consumer holograms, how are they getting enough resolution to map micrometers of stress on giant airplane wings?
For these highly demanding industrial applications, they often bypass standard silicon sensors entirely.
They just skip silicon.
Pretty much. Instead, they use photorefractive crystals. A prime example mentioned in the analysis is bismuth silicon oxide, or BSO.
How does a crystal bypass the pixel bottleneck?
Well, instead of a digital grid of discrete individual pixels capturing light, these crystals respond to light holistically.
Okay, holistically.
Yeah. When the interference pattern hits a BSO crystal, the light physically forces electrons inside the crystal lattice to shift out of their normal positions.
Oh.
I know. This creates a smooth, continuous electrical map of the optical phase inside the crystal itself. It is entirely analog.
Because there are no distinct pixels.
Exactly. Because there are no distinct pixels, the resolution is vastly superior. It easily handles complex, rough surfaces like aerospace composites. It reduces the visual static known as speckle noise. And the best part is the crystal can be erased with a flash of light and reused infinitely.
That makes so much more sense. The crystal is basically acting like an ultra-high-resolution analog sponge for the light waves.
That is a perfect way to describe it.
So we've established that holography is vital for measuring rigid industrial materials like metal and carbon fiber. But the expert analysis takes a sharp turn into biology. And well, measuring soft, squishy, living biology seems like a completely different challenge.
It is a different challenge for sure, but the core principles remain the same. And they've created an entire subfield called digital holographic microscopy, or DHM.
DHM.
Yes, and it's completely transforming how scientists study living cells.
Because the historical problem with standard microscopy is that a lot of living cells are almost entirely transparent, right?
Right.
They're essentially tiny bags of water.
Yeah.
So if you put them under a normal microscope lens, you can barely see their internal structures. Scientists usually have to inject them with chemical dyes to create visual contrast.
Which introduces a massive variable into your experiment.
I'd imagine so.
Yeah, injecting a living, fragile cell with a synthetic chemical dye is highly invasive. The dye itself can alter the cell's natural behavior, cause artifacts in your data, or, simply kill the specimen outright. You're no longer studying the cell. You're studying a poisoned cell.
But holography removes the need for dyes entirely.
Because a digital hologram records the phase of the light. See, when light passes through a transparent cell, it slows down slightly depending on the internal density of the cell's different organelles.
Oh, I see.
Even if the cell looks perfectly clear to the human eye, the hologram captures the exact microscopic delay in the light wave.
The phase delay.
Exactly. By mapping that phase delay, scientists can visualize the internal density of the living cell with stunning contrast, completely non-invasively. They can watch cells move, divide, and interact in their totally natural, unaltered state.
That is an incredible tool for cellular biology. And the document outlines an even more advanced medical application called optical coherence holography, or OCH.
Yes, OCH is fascinating.
The text says OCH allows doctors to image highly scattering living tissue, penetrating over 1 millimeter deep. What does highly scattering mean in this context?
Think about shining a flashlight through a glass of milk.
Okay, sure.
The milk isn't solid, but the light hits all the tiny suspended particles and scatters in every possible direction, creating a blinding white wall.
Right, you can't see through it.
Human tissue acts the exact same way. Light scatters, making it impossible to see deep into the flesh with a standard camera. Optical coherence holography uses specific algorithms and interferometry to filter out all that scattered noise.
It just strips it away.
It does. It only reconstructs the light waves that travel directly back from the deep tissue. This allows doctors to optically penetrate over 1 millimeter into living flesh without making a single incision, which is a massive leap forward for early cancer detection and non-invasive surgical planning.
The market data in the source document completely validates that medical focus. It highlights that healthcare is the fastest growing sector for holographic technology, making up 23.3% of the global market.
It's huge.
Surgeons are just pouring money into real-time 3D visualization. Geographically, the Asia-Pacific region is dominating, holding nearly 37% of the market share due to heavy investments in the underlying hardware, like micro-LEDs.
Which makes sense.
But if medical and industrial applications are so dominant, I have to ask about another statistic. Retail holds a 22% market share. How is a shopping mall competing with aerospace engineering?
Well, they're competing by utilizing what the document diplomatically calls subterfuges.
Let's call them what they are, optical illusions. Because when I walk through a trade show and I see a glowing 3D sneaker floating in midair, You're telling me that is not a true hologram.
It is absolutely not optical holography. It does not use wave interference, and it does not use diffraction. Let's look at the most common retail illusion, the hypervenz displays.
The ones that look like floating images.
Yeah, they look incredibly futuristic, but physically, they're essentially high-tech desk fans. They feature spinning blades lined with bright LEDs. As the blades rotate at extremely high speeds, the LEDs flash in rapid sequences, drawing flat 2D slices of an image in the air.
But my brain sees a solid 3D object.
Because of a biological quirk called persistence of vision.
Okay.
The human eye just can't process images fast enough to separate the individual flashes. Your brain blurs all those spinning 2D slices together into a single floating illusion. It is a modern, high-speed zoetrope.
A zoetrope. Wow.
The document also mentions Voxon VLEDs, which are more sophisticated volumetric displays. They physically sweep an array of LEDs back and forth, generating millions of individual dots of light, or voxels, in a physical 3D space.
So they are actually painting light at different depths.
Yes, which is an amazing feat of engineering, and it allows you to walk around the image without wearing 3D glasses. But they are generating distinct points of light, not recording and recreating an unbroken wavefront of optical phase.
If the mall displays are just spinning fans, where does the average person actually interact with a real diffraction-based hologram in their everyday life?
Look in your wallet. The small rainbow-colored foil stickers on your credit cards, or the metallic security strips woven into paper currency.
The anti-counterfeiting tags.
Exactly. True wavefront recording captures information down to the microscopic wavelength level. To forge one, a criminal would need the original master hologram and a highly specialized laser laboratory. They are incredibly difficult and expensive to fake, making them the ultimate security seal.
But getting beyond tiny stickers, what is actually holding back the public adoption of the real room-sized holographic technology?
The document lays out several massive hurdles we still face. We already discussed the restricted field of view caused by the pixel bottleneck.
The fat marker problem.
Right. Beyond that, creating sufficient brightness is a major issue. True holograms often appear dim under normal lighting. The hardware costs for high-density spatial light modulators are astronomical, and the industry currently lacks a mature supply chain to manufacture these components at scale.
So to recap all of this for you listening, this has been an incredible journey. We started by looking at Dennis Gabor back in 1947, who accidentally invented the mathematics of capturing the optical phase of light while trying to fix electron microscopes. We saw how the dream of digital holography is currently bottlenecked by the physical size of pixels on camera sensors, a limit defined by the Nyquist theorem.
We also explored how, despite the hardware limitations for entertainment, the industrial applications are thriving. Engineers are using holographic interferometry and vibrometry to map micrometer-scale stress on vibrating airplane engines.
And in biology, digital holographic microscopy is letting scientists observe living, transparent cells without poisoning them with chemical dyes, while advanced algorithms let doctors see deep into living tissue. So what does this all mean for you?
A lot, actually.
For one, the next time you walk through a store and see a floating 3D logo, you'll know exactly why it's just a clever illusion relying on the biological slowness of your own eyes. But more importantly, you'll understand that true holography is quietly working behind the scenes. It's verifying the money in your pocket, making sure the wings on your next commercial flight don't have hidden fractures, and advancing the frontiers of cellular medicine.
This raises an important question, though. A philosophical scenario born directly from the physics we've explored today.
Oh, I'm ready.
We know we're currently restricted by hardware, the inability to manufacture dense enough pixels. But manufacturing technology continually shrinks. Let's project forward to a point in time when our digital sensors and spatial light modulators finally cross that threshold, achieving the density required for a massive field of view.
A future where the silicon finally catches up to the mathematics.
Precisely. If a true digital hologram flawlessly records and diffracts the precise optical phase and intensity of light bouncing off an object, then physically, the light wave hitting your retina from that hologram is fundamentally identical to the light wave that would hit your retina from the real object.
So the biology of your optic nerve would literally be incapable of telling the difference.
Exactly. Which means, once we cross that engineering horizon, will our brains even possess the capacity to distinguish a reconstructed light field from physical reality? If we reach a point where a digital projection and reality are optically indistinguishable, what happens to the entire concept of seeing is believing?